All right, so this is our first lesson, our unit on waves, sound waves, and optics. So we're going to start off in this lesson by looking at the properties of waves, what waves are, and what do we use to describe waves. So some announcements, we have a quiz next Wednesday on February 10th. Our agenda for today, what is a wave? We've already been introduced to a wave very slightly in our inquiry activity, but now we're going to get a more formal notion of what a wave is, and that includes looking at the properties that affect the wave speed, aka how fast a wave travels. That includes looking at the anatomy of a wave. I have it listed as wave phenomena here, but better said, this would be listed more as kind of like the anatomy of a wave, what makes up a wave. We'll look at the wave speed equation and how to apply the wave speed equation, and we'll look at classwork 7.1 for remainder of class. So what is a wave? Part 1. All right, so a wave is a movement of energy from one location to another. All right, so if a rock hits a body of water, that rock will transfer energy into the water, and that energy will transfer outwards and from where the rock hit in the form of waves. So the waves that you see produced by a rock is representative of the energy being transferred from the rock and by the waves from the rock to wherever the waves end up. So waves require a medium such as water or air for energy transfer to occur, since energy is transferred by collisions in the medium. Okay, so the same way that if I'm speaking right now, there's energy being transferred from my vocal cords into the computer recording system. This is occurring because my vocal cords are colliding with air molecules right next to them. Those air molecules collide with air molecules, and that collisions go on forever and ever and ever. Well, not forever and ever, but until the sound wave reaches its source. At which point, okay, or excuse me, not the source, but reaches its destination. At which point, the energy from my vocal cords is transferred to the destination. All right, without considering, of course, sound intensity. All right, so there are two types of waves that we're going to look at in this unit. We're going to look at transverse waves, which means our medium oscillates perpendicular wave's direction. So a transverse wave would be like a water wave. A water wave moves from left to right or moves right to left, depending on where your source of the water wave is. And as the wave passes through a certain point, the point rises up and down. So the water itself, that point will rise up and down while the wave itself moves left to right. So we have that any point in the water will move vertically while the wave moves horizontally. Okay? And then we have a longitudinal wave. A longitudinal is where a medium oscillates parallel to the wave's direction. That's like if you send a pulse down a slinky, the slinky will compress and expand in the horizontal direction as the wave passes through in the horizontal direction. So the medium oscillates in the same direction as the wave's motion. All right. And then here's a demonstration of what we are talking about. Okay, so for a transverse wave, B would be an example of a transverse wave. We can see that the slinky oscillates up and down as the waves head from left to right or right to left. In this case, it would head from left to right. So as our wave heads from left to right, the slinky is going to oscillate up and down, perpendicular direction motion. Now for longitudinal, all right, such as this, as we send pulses in this horizontal direction right here, so we have these horizontally traveling pulses. All right, we can see that the medium, the slinky, shrinks and expands and compresses, indicating to us that the slinky is oscillating in the same direction as the motion of our waves. So here we're going to look at wave properties and wave speed. Okay, so wave speed is affected by the following factors: the density of the medium. The reason being is that there's an inverse relationship with wave speed. The reason being is that the more dense something is for a given volume or given length, that means there's more mass and thus more inertia. And we know inertia is a resistance to a change in motion. So if we have more mass due to an increase in density, then there's going to be a stronger resistance to waves traveling through that material, and thus waves will travel slower. All right. And then the last one is tension, okay? So tension, if you imagine it's like a guitar string, the more tense a guitar string is, the faster the wave on the guitar string will travel. And that's because the more tension you have, there's going to be a stronger force acting on the guitar string, and that's going to result in a faster motion for your guitar string, and thus a faster wave traveling along, okay? So now we're going to look at some wave properties. Oh, guess I didn't have any animations here. So now we're going to take a look at wave properties, okay, in terms of distances and physical space. So the first one we're going to look at is what we call amplitude. So amplitude is a measure of the energy carried by a wave. For a transverse wave, it is the maximum height above a crest, above or below the rest position. Our rest position is where our wave would typically be at. So for a water wave, the rest position, okay, would just be if we had still, calm water, okay? And then the amplitude is going to be the maximum height of our water wave when the water is disturbed, okay? Maximum height above this rest position. All right, so the amplitude when we're above the rest position is called a crest, and then when we're below the rest position is what we call a trough. Okay, crest like a mountain, and then trough like a feeding trough, the bottom of a feeding trough, for those of you who are familiar with farming. Okay? For a longitudinal wave, it is the area of maximum compression for the wave. So if we look right here where our spring is most compressed at is where we're going to have an amplitude at. Okay? And then wavelength. All right, so another feature we use to characterize a wave is what we call a wavelength. So a wavelength is a distance between two identical points in a wave. Oftentimes this is crest to crest or trough to trough. Another way that you can think of this is that the wavelength is a distance required to complete one full cycle of a wave. So for example, if we start out right here, okay, we can notice we're going to go through one full cycle, meaning one crest and one trough, and end up right back here. All right, so this right here, this distance from here to here would be our wavelength. Notice how they are identical points, how our wave comes through the rest position and above right here, and then when we reach right here, our wave is coming back through the rest position again and above. So these 2 points, the distance between them is a wavelength. If we use 2 troughs, all right, it's going to be the distance between 2 successive troughs, and then if we use 2 crests, it's going to be the distance between 2 successive crests. Okay? All right, and then here's just a larger diagram of our wave properties, okay? So now let's look at wave properties in terms of time, okay? So we need to define period and frequency. All right, so period is the amount of time it takes one full wavelength to pass a point, okay? So if we had like a water bob, if we had a bobber, like a fishing bob in water, a period would be the time it takes for a crest, for 2 crests to pass through, better said, I'm messing up a little bit here. If we had a fishing bob that started out on a crest of a wave, then the period would be the time it takes for another crest to pass through the fishing bob, okay? So it's the amount of time it takes for one full wavelength to pass a point, okay? Frequency, on the other hand, is the number of full wavelengths to pass a certain point over a certain time interval. So it's the number of cycles that we have over a certain time interval. So we can make sense of that in terms of frequency, in that frequency asks how often something occurs. With frequency in physics, we're asking how often does a wave pass through a certain point over a certain amount of time. So the unit we use for frequency is Hertz, named after the German physicist Heinrich Hertz, okay? And the big thing to note is that period and frequency are reciprocals of one another. So if we know frequency, we can find period and vice versa. Okay, frequency is equal to 1 over our period t, and then t as a result is going to be equal to 1 over our frequency f. They're reciprocals of each other. Okay, and all this is a little bit abstract. I'm going to have an example here in a second here that I'm going to use to illustrate period and frequency. Okay. So next we come up to the wave speed equation. Okay. So wavelength, frequency, and wave speed can all be connected by the following equation. The following equation tells us that wave speed equals frequency times wavelength, okay? And what's important about this equation is it tells us that if wave speed is constant for a given density and tension, remember wave speed is dependent on density and tension. So if both of those are constant, our wave speed will be constant. And if our wave speed is constant, there's going to be an inverse relationship between frequency and wavelength, meaning that if frequency goes up, wavelength will go down, and if frequency goes down, wavelength will go up. So an inverse relationship, okay? A way to think about this is like a slinky coil, all right? If you think about like a slinky coil as a wave and the distance between each coil as a wavelength, then as a slinky compresses, the coils get closer together. So the wavelength is decreasing, but there's more coils in a certain amount of space, meaning our frequency is increasing. So we see there's an inverse relationship between wavelength and frequency. Okay? All right, so a way to visualize all these abstract quantities we're talking about is to think about a wave like a roller coaster, okay? So the wavelength is the length of the track, all right? So the length of the track from where you start all the way to when you end back up all the way until you end back up where you start is the wavelength, okay? And again, just as with wavelength, we can choose any point on our wave, any point on our roller coaster to measure so long as we come back to an identical point. So if I decide to measure from the top of my roller coaster hill, that's perfectly fine as long as I end right back at the roller coaster hill. I will get the same wavelength, the same roller coaster track length as if I were to measure from the starting station and then back to the starting station, okay? The wave speed is how fast the roller coaster moves along the track. And then the frequency is how many trips are completed over a certain time, while the period is how long a single trip lasts. And so to show you how those two are the inverses of each other, the reciprocals of each other, okay, I'll consider your following example, okay? So let's say a roller coaster completes 3 trips per 60 seconds, okay? So as a result, okay, that means we are going to be completing 1 trip every 20 seconds, 3 over 60. So that means our frequency is going to be 1 over 20, okay? However, at the same time, because we're completing 3 trips in 20 seconds, we know that 20 seconds is going to be the period for 1 trip, okay? 60 divided by 3. So the period of our roller coaster is 20 seconds. So our frequency is 1 over 20, and our period is 20 seconds. So we can see that frequency and period are the inverse of each other, okay? All right. And then for a consistent medium, meaning a uniform density and tension, the wave speed is going to be constant, and frequency and wavelength have an inverse relationship. So in terms of our roller coaster example, this is like shortening the track. The track remains the same, and thus the wave speed too, but a shorter track means it can complete more trips per minute. So the frequency is going to increase as a result of the wavelength decreasing. All right, so let's look at some math examples here of analyzing waves. So a camera on a dock records 12 water waves passing by in 36 seconds. We ask first for A, what is the frequency and period of this wave? All right, so what we take note of right here is the frequency describes how many waves are passing through a certain amount of time. So that's going to be given by 12 divided by 36, the 12 amount of waves passing through in 36 seconds. So our frequency is going to be 12 over 36, or 0.3 repeating hertz, okay? From the diagram, okay, B asks for what is the wavelength. From the diagram, we can see that our wavelength is going to be 8 meters because it's the distance between two identical successive points. So distance from the crest to the next crest, which is 8 meters. It is not going to be 4 meters because 4 meters is the distance from a crest to a trough, which is 1/2 of a full wavelength, 1/2 of a full cycle, okay? And then lastly, C asks what is the speed of this wave. So we need the wave speed equation, which is going to be wave speed equals frequency times wavelength. And so that's going to be equal to 0.3 hertz, our frequency that we found in A, times 8 meters, our wavelength found in B, which is going to give us 2.67 meters per second. Okay? And this is how we carry out a standard problem for analyzing waves. Some things of note, whenever we ask for frequency and period, okay, if you don't have wave speed or wavelength, you're going to find that by using how many waves you're passing through a certain amount of time, okay? For B, if you have a diagram, you can always find your wavelength from the diagram. And then for C, whenever it asks for wave speed and it gives you wavelength or frequency like you found in A and B, you're going to use the wave speed equation. Or vice versa, if you're looking for, say, wavelength and you know frequency and wave speed, you're going to use the wave speed equation, okay? So if you have wave speed or are looking for wave speed, you're always going to use the wave speed equation. All right, example 2 of analyzing waves, okay? A wave generator produces 10 wave pulses per second. Each pulse moves at a speed of 3 meters per second. What is the wavelength of the wave? All right, And now we're looking at how to apply physics and mathematics to model these wave generators you may see at a wave pool. Okay. Ooh, what is this upside down delta? Do we have a gradient here? Ooh, I haven't seen that notation since Calc 3. I'm so used to the covariant derivative notation, or the covariant partial derivative notation, Minkowski flat spacetime. Ooh, man. Special relativity stuff here. All right. I'm not sure. Maybe, maybe not. I'm overthinking this. And now I'm losing my audience. All right, let's get back to, I'm going down a rabbit hole and I'm losing myself here as well. So let's get back to a problem at hand. All right, so we're asked to find the wavelength of the wave. All right, we know the wave speed, so we need an equation that relates wavelength to wave speed, which is going to be the wave speed equation. Wave speed equals frequency times wavelength, okay? We know the wave speed is 3 meters per second. In order to find our wavelength, though, we still need our frequency. But the problem does not tell us our frequency specifically, okay? But we can figure it out because we know frequency is the amount of waves passing through a certain point per second. So we can look here and see that 10 waves pulses per second is going to describe our frequency. So F is 10 hertz, okay? So as a result, we're going to have V equals 3 meters per second, F equals 10. So we're going to have 3 equals 10 times lambda. And as a result, solving this equation divided by 10 is going to be lambda equals 0.3 meters, okay? Lastly, let's go through a check for understanding problem, all right? A series of 8 water waves pass by a buoy in the span of 32 seconds, with the distance between successive crests being 4 meters, okay? We want to know, A, what is the period of this wave, and then B, what is the speed of the waves, all right? So please pause this video to work on this problem, and then we are going to continue on right now. So please pause this video if you want to work on this problem without seeing the solution. Okay? So A asks us for what's the period of this wave. So it takes 32 seconds for 8 waves to pass by, which means it is going to be 8 seconds per wave. So our period, it takes 32 seconds for 8 waves to pass by, which means it's going to be 32 divided by 8, 4 seconds per wave. So our period is going to be 4 seconds. Okay? So our period is going to be 4 seconds, and then as a result, our frequency is going to be the reciprocal of that. So we're going to have 1/4 hertz for our frequency. A asks strictly for the period, but for B, it asks for speed of the wave, so we're going to need to know our frequency, so we take the reciprocal of the period to find 1/4 hertz. We could have also found the frequency first by taking 8 waves and divide by 32, and then take your reciprocal to find our period. So either way works. Either way, you're going to get that your period is 4 seconds, your frequency is 1/4 hertz. For B, all right, we need to use the wave speed equation. So wave speed is going to be equal to frequency times wavelength, which is going to be 1/4 hertz times 4 meters. Our wavelength is 4 meters, the distance between successive crests. So as a result, our wave speed is going to be 1 meter per second. Okay? And these are the basic mechanics of waves and how we analyze waves using the wave speed equation and the frequency and reciprocal equation.